Welcome and thank you for joining us for the fourth Agro Lunch and Learn webinar of 2022. This webinar series is only possible through the generous support of from Eurofins Agroscience Services. We thank Eurofins very much for their continuing sponsorship. My name is Salito Sumlong from Agro Authority. I'm an officer for the ISAA Agrochemical Network, and I'm an executive committee member for the American Chemical Society Agro Division. I'll be serving as moderator for today's webinar. Attendees should use the Q&A tool, I believe on the bottom of your screen, to submit their questions and comments, which will then be answered at the end of the presentation. Before I introduce our speaker, I'll highlight the benefits of becoming an Agro member. Agro pays enormous benefits by enhancing your science, building your scientific network, and supporting your professional development. Please go to agrodiv.org and click on Become a Member to become an affiliate for $20 a year, regardless of your membership status with the American Chemical Society. I'd also like to inform you about the upcoming ACS Spring National Meeting in Indianapolis in March 2023. This is a rare opportunity to experience the Agro content at the spring meeting. We traditionally operate in the fall meeting. Please submit abstracts at maps.acs.org for our 4 sessions by October 17. On Wednesday, the 29th, during the spring meeting of March, Corteva is offering to whisk you away to their campus just minutes away for an Agro Division social event. If you have any questions about the programming, I know that COVID is a fluid thing, so policies are going to change between now and then, I'm sure, and presentation formats. Contact Aaron Gross of Virginia Tech, our program chair for both the spring meeting in Indianapolis and the fall meeting in San Francisco. Not an easy task by any stretch. Both today's speaker, Jason Wall, and I represent the ISAA Agrochemical Network. He was a generous contributor to our ISAA Symposium, which last got together in April in Bordeaux. The symposium is the preeminent global conference on agrochemical adjuvants, formulations, and inerts, and will convene again in mainland Asia for the first time in 2025. In the meantime, please consider joining ISAA as a member for less than $30 a year at www.isaanetwork.org to unlock key new connections in this specialized field, access ongoing scientific conversations from the last symposium, and access the archives from previous symposia. Now I'm proud to introduce our speaker, Jason Wall. Dr. Jason Wall is an applications team leader in the crop care division of Croda Incorporated. He joined Croda in 2016, working in the areas of pesticide and adjuvant formulation development and new product development. He has experience in developing both solid and liquid formulations from the bench scale to full-scale production. Prior to joining Croda, he spent 15 years at DuPont, with the last 7 in the crop protection group. He has a BS in chemistry from Virginia Tech and a PhD in chemistry from Virginia Commonwealth University, with a focus on salt gel chemistry and nanoparticle synthesis. And now to start the impact of adjuvant and formulation type on UAV application, a man who wears bow ties better than I do, Jason Wall.
You did not ask if you could use that incredibly awkward looking picture that I taken at the ACS meeting. All right, you want me to share my screen?
Sure. You can override me.
Sure.
There we go.
Hopefully this will work. Presentation mode. It's a little slow. All right, so can you see my presentation in actual presentation mode?
Not yet.
Okay.
We are good.
All right. Thanks for the introduction, Salito. Today I will be talking about the impacts of adjuvants on UAV application, and the work that follows in this presentation was done by a big group of people here at Croda, Inc. The first group is all in the US, and Allison Selmer is down in Latin America. But what I'm going to talk about is a little bit of background on UAV applications, if you're not familiar, and then what we did along the way in characterizing the impact of formulations on UAV applications and adjuvants on the tank mixes that are used in UAV applications. We followed that with a small field study. It's not extensive, but it will give an idea of some of the effects you might see, and then I'll wrap up some conclusions. Now, if you're not familiar with UAV application, the UAV stands for unmanned aerial vehicle, also sometimes referred to as drones. And these are becoming more prominently used in certain geographies on the globe. And due to a variety of reasons, some of the advantages of using drones or UAVs is it reduced need for labor inputs. You can get more done. Say if you were using backpack sprayers, you can get more done with a UAV maybe than having a bunch of people out in the field physically spraying.
Jason,
Yes.
For a sec, could you lean into your microphone a bit? There you are.
Yes, sorry. They also allow ease of application on complicated terrain. So if you've ever visited a vineyard, those are often planted in very picturesque hilly landscapes, which can be difficult to get in there and manually spray. And then it can extend your application period. You don't have to be able to see as well, because you can digitally map out your field and then spray it at night. Or if the ground's too wet to bring a tractor into your field, you could apply with a drone, which will never touch the ground, at least in the place where you're spraying. So there are some advantages to using them, and there are some key differences that need to be accounted for when comparing UAV application to ground application. The most obvious, the one that jumps out, is the low spray volume typically used. A typical drone is a small electric motor powered aircraft, and they typically don't have a large spray tank that they can carry large volumes with. So you tend to try to cut the spray volume on your application as much as you can. And it can be cut anywhere from, say, 5 to 25 liters per hectare versus the 100 to 150 liters per hectare of a typical ground application. And because you have a lower spray volume, but you're applying the same amount of pesticide, the concentration in your spray volume is typically a lot higher. And so that can introduce some complications. In addition, there's typically no agitation in the spray tank. There's maybe some sloshing around due to the drone flying around above the field, but there's no mechanical agitation of the tank. So you need to make sure that your formulation is stable for the amount of time it's going to take to spray out that tank. Since it's a small tank, it typically doesn't take that long, but you do need to have that stability. And this is some data from an ASTM presentation in 2019, just showing the increase of the use of drones in China. And so, believe it or not, there is a labor shortage for an agriculture in China. And so drones are taking up some of the slack in the labor shortage, because they allow application to a lot more acres with fewer people. So you can see these numbers. It translates to about 43 million acres in 2018. So I imagine this trend has only continued, and so there's probably more than 43 million acres being applied with UAVs in China today. So the applications are becoming more important, and so we do need to consider the complications of applying with UAVs. And there's several challenges. The first that comes to mind when we were looking at this is the potential for off-target movement and drift. Because you're applying it per acre, you tend to use a very fine nozzle, very fine spray nozzle, to compensate to get the coverage you need. But if you've been involved in any of the drift discussions over the last few years, you know that small droplets tend to be more influenced by wind and are more likely to move off target than larger droplets. That's why they use coarser nozzles and adjuvants that increase the droplet size to reduce drift. In addition to using very small droplets, they're also spraying at a much higher height above the canopy, so 1.5 meters maybe above the ground. And so there's much more potential for the droplets to move before they intercept whatever their target was. So there's certainly a concern about drift. Also, because the tank mix tends to be more highly concentrated, there's also the potential for there to be more interactions between formulations and adjuvants in the tank, such that you might have compatibility issues. And those could be more pronounced at the higher concentrations. And then if you take those two things together, it might result in inferior efficacy. The lower spray volume might lead to lesser coverage or more off-target movement. And the droplets that are that small can actually evaporate before they even reach their intended target. So while UAVs offer flexibility and some advantages, there's also some challenges that we need to understand as the use of UAVs increase. So as I mentioned before, we looked at the effect of formulations and adjuvants on some kind of surrogate UAV tank mixes. These aren't necessarily tank mixes that are used currently in the field, but they exemplify a bunch of different formulation types and different adjuvant types and their effect on the physical chemical properties of tank mixes. So we looked at the dynamic surface tension of the tank mix, the equilibrium surface tension, the contact angle, and the spreading of the droplets. And then we looked at the behavior of tank mix droplets as far as retention, what the deposit looks like, and the percentage of driftable fines that are formed in spraying with a typical fine spray nozzle. And then we follow up with a small field study just to look at biological efficacy. A word about the actual formulations that we used. We use an unloaded SL. So that means simply an active ingredient dissolved in water with no added adjuvant. And in this case, it's glyphosate IPA salt. And the drone concentration was 22.7% AI in water, and the ground rate was 2% AI in water. We used what we called a loaded SL, which is a glyphosate potassium formulation with a built-in adjuvant. And we use that at the same rates as the unloaded SL at 22.7% in the UAV concentration, then 2.5%, AI in the ground rate. And we looked at a suspension concentrate used at 6% or 0.3%. It's a strobel urine fungicide suspension. And then we looked at an EC at 3% and 1% of a strobel urine, and then a CS formulation, a capsule suspension at 12%, same stroke. So we looked at a variety of formulations, the typical formulation types you might encounter when wanting to use a UAV. The adjuvants evaluated, we evaluated two different adjuvants, and we don't talk about the chemistry of the adjuvants specifically, but they're generically a polymer-based DRA, a drift reduction adjuvant. And it is a blend of an anionic surfactant and a high molecular polymer. And it tends to reduce small droplets in the spray and improve retention and wetting. And then we have an emulsion-based DRA, which is a blend of a non-ionic surfactant and a vegetable oil-derived fatty ester. And it also reduces the amount of small droplets in the spray, and it improves retention, spreading, and uptake. And these have been evaluated in ground applications. So we know what to expect when we use these adjuvants as part of a ground application program. Both adjuvants contain an ethoxylated sorbitan ester NIS. If you're familiar with Croda, you probably can guess about what that is. And both adjuvants have been validated through ground-based testing. So we have looked at these. We know how they perform in typical ground concentrations and how they affect the properties of those spray mixtures. But we wanted to look at both the spray mixtures without adjuvants and with adjuvants to see if there's any interactions that might be surprising based on the increased concentration of typical UAV application rates. Now, if you're not familiar with DRAs, drift reducing adjuvants, then the high molecular weight polymer tends to induce the elongational viscosity and thereby reduces small droplets in the breakup of the spray sheet. And they tend to be less influenced by typical tank mixes in that they're used at very low rates, so they tend to be compatible with a wide variety of tank mixes. The other DRA we're using is a soft water immiscible droplet. In our case, it's an emulsion, but they can be from a variety of sources, from emulsions to vesicles to low HLD surfactants. The issue that these sometimes encounter is that they can be influenced by the efficacy can be influenced by the components of the tank mix. Since you're emulsifying an oil and putting a surfactant in there, the surfactants that are used as co-formulants in typical formulations can interact with the adjuvant and inhibit its ability to control drift. So that's why we want to look at two different DRAs with two different mechanisms of action. And so this might be a little bit repetitive, but yeah, we looked at the physicochemical properties of tank mixes. And this is just saying the methods we used. We used cruise tensiometers, and in the dynamic surface tension case, we used the maximum bubble pressure method. And in the equilibrium surface tension case, we used the Wilhelmine plate. For contact angle, we measured it with a goniometer made by Attention. And for spreading, we used a modified ASTM method. Typically, the ASTM method uses parafilm stretched over a Petri dish, but we actually use polystyrene Petri dishes. And then we looked at the behavior of tank mix droplets. We put deposits on glass microscope slides, which is maybe not the best surrogate for a leaf surface, but we can compare them apples to apples. And then we looked at droplet retention using our droplet on demand generator, ejecting droplets aimed at a particular plant surface and then capturing those droplets as they impact the surface with a high-speed video camera. And we used our low-speed wind tunnel to evaluate the droplet size distribution of the tank mixes. And finally, again, we followed up with a small field study. So I'm going to jump into the data, and you don't have to be able to read any of this because we'll go through it individually, but I do want to talk about the layout or the layout of the data and all the slides going forward. The formulations are segregated by color. So the yellow, the dark blue is water. The yellow is the unloaded SL, the glyphosate IPA with no adjuvant built into the formulation. The green is the loaded SL, so a glyphosate potassium with a built-in adjuvant. The orange is the suspension concentrate, which we don't know the formulation components of. It is a commercial formulation. The EC is in light blue, and we also don't know that formulation. And the red is the capsule suspension. So those colors will be carried through for the whole presentation. So hopefully that helps decode some of the data as we go forward. And the other thing to mention is that the dynamic surface tension data is presented as the surface tension at 200 milliseconds of surface age. If you're familiar with the literature, some people use that as a surrogate for determining retention behavior. So measuring the surface tension at 200 milliseconds gives you an indication of what kind of retention behavior you might see with your spray. So moving on to the unloaded SL, this is the data as it is. And so you can see that the unloaded SL at 2% and 22.7% both have very little effect on the surface tension at this surface age. And then addition of adjuvants, the emulsion DRA reduces this surface tension under these conditions. And then the polymer-based DRA also reduces the surface tension. So in this situation where you have no surfactant in the formulation, it's not surprising maybe that an addition of a surfactant containing adjuvant will reduce the surface tension at 200 millisecond surface lifetime. Moving on to the loaded SL, the surfactant in the formulation plays the dominant role. So there's no real effect of the adding an adjuvant to the surface tension of this surface lifetime. There's enough surfactant in the formulation to do the work at this point. Moving on to the suspension concentrate, at a ground rate, there's very little reduction in surface tension. And then adding adjuvants, either the emulsion or the polymer-based, reduces the surface tension somewhat at this surface age. However, at a UAV type concentration, the co-formulants in this formulation are doing a lot of work in this case, and they're reducing the surface tension at the surface age to the extent that addition of an adjuvant doesn't further reduce the surface tension. So that right there is a significant difference between ground and UAV concentrations with or without an adjuvant. Moving on to the EC, once again, ECs tend to have a lot of surfactants to form that spontaneous emulsion, so you don't see a lot of effect of adding an adjuvant to either the ground rate or the UAV rate. There's a little bit of noise in the data, but overall, there's very little effect of adding an adjuvant to this EC in terms of dynamic surface tension at the surface age. And then similar to the EC, we don't have the ground rate in here, but at the UAV rate, there's no effect of adding an adjuvant on the dynamic surface tension at the surface age, which, not surprising, a capsule suspension typically produced by forming an emulsion and then doing some sort of interfacial polymerization. So there's probably a lot of surfactant in this formulation. So there's not much else that the adjuvants can do for the dynamic surface tension. So taking a step forward and looking at the equilibrium surface tension, the colors are the same for the formulation types. So you can see that there's a wide variation between, big difference between water in the formulations. But the simple presence of the organic salt in the SL reduces the equilibrium surface tension to relatively low values. So it's not dynamic, but given time, the surface tension will equilibrate to a relatively low value. But even at this point, addition of an adjuvant reduces that a little bit further. So if you think about equilibrium surface tension in the way that the deposit forms after initial impact, influencing that, then addition of an adjuvant can have an effect here. And in the case of the loaded SL, where we didn't see an effect on the dynamic surface tension, we do see somewhat of an effect on the equilibrium surface tension with the addition of the emulsion-based DRA. So the polymer-based DRA, not so much of an effect. However, the emulsion-based DRA has a somewhat significant effect on the equilibrium surface tension after that droplet has been sitting, or after the droplet would have been sitting on the leaf. The SC shows actually a pretty significant reduction in surface tension at the equilibrium time point, even at the ground rate. So there's not really any difference between the ground rate and the UAV rate in equilibrium surface tension. There was a big difference in dynamic surface tension. So it's a surfactant concentration effect. There's not as much surfactant in the ground rate, but once you give it time, those surfactants will move to the interface and reduce the surface tension. But again, adding an adjuvant can reduce the surface tension somewhat. It's not a huge decrease, but it could be significant depending on the application. And then with the EC and the CS, just grouped the data together because there's really no significant effect of the adjuvants on the equilibrium surface tension. There's some noise in the data, but in general, they're pretty much the same. And if you, sorry, there's no boxes on this one, but yeah, so the 1% EC is a little bit higher than the 3%, but there's no real effect from adding an adjuvant to either of these formulations on the equilibrium surface tension. And the next data set we'll look at is the contact angle. And it's interesting that if you think about equilibrium surface tension in the sense of how it affects the deposit formulation, well, it doesn't line up perfectly with the contact angle. And I think it's pretty well known that equilibrium surface tension can influence contact angle and spreading, but it doesn't tell the whole story. So we see some of that effect in this data. And so the equilibrium surface tension of the unloaded SL was pretty low, but it doesn't have a significantly different contact angle than water by itself. So even with that surface tension, it's not showing an effect on the contact angle, whereas adding either adjuvant significantly reduces the contact. So adding an adjuvant at a ground rate does a good job. However, at the higher concentration, at the 22.7% loading, without any surfactant, there's a pretty good reduction in the contact angle. So it takes a higher concentration of adjuvant to actually reduce that further. So the typical maybe ground rate of the emulsion DRA doesn't have much of an effect on the contact angle at the UAV concentration, but a higher concentration does have an effect. So it's an important difference between ground and UAV application. And then with the loaded SL, unsurprisingly, there's a lot of surfactant in this loaded SL. So the surfactants built into the formulation continue to dominate the behavior. The contact angle is significantly less than water with or without the adjuvant. And then with the suspension concentrate, we saw that the equilibrium surface tension was pretty low for both rates, and so we see a reduction in the contact angle, and that's due to the presence of surfactants in both formulations. In the ground rate, they take longer to diffuse because the concentration is lower, but they still have an effect. But adding the either adjuvant to the ground rate reduces the contact angle, and adding the adjuvants at some rates reduces the contact angle a little bit from the UAV concentration, but maybe not as much as you might expect. And in this case, there's no effect on the concentration of the emulsion-based DRA, where previously there was an effect. So there's different things happen in different situations with different formulation types, and that's kind of why we generated this data. We wanted to have a good understanding of what do we need to look for when we're building adjuvants for formulations or when we're building techniques. And then in all cases with the EC, there's a low contact angle both at the ground and the UAV rate, and the addition of adjuvants, again, in this case, does not show any effect. And then the same story with the CS, which you probably noticed by now. The CS and the EC behave very similarly. Excuse me. most likely due to the presence of the high concentrations of surfactants. And then moving on to the spreading data, where this is the droplet area after 5 minutes. So it's a long experiment, but it gives significant time for the surfactants to have any spreading effect that might show. And in this case, both the formulations unloaded at ground and unloaded at UAV concentrations do not spread significantly more than water. But addition of the emulsion-based DRA shows a significant increase in the spreading. So while the polymer-based DRA does not improve spreading to a large extent, the emulsion-based DRA shows a significant. And then here's a case where the adjuvants actually do something even with a loaded SL, where the loaded SL shows pretty good spreading by itself, but the addition of the oil-based adjuvant improves that spreading, and that might be due to the fact that, or the emulsion-based has an oily component to it, which might interact differently with hydrophobic surfaces than the surfactant built into the loaded SL. So, this is a case where the previous data said you don't even need an adjuvant, and this data says, well, maybe we do want an adjuvant if we need a specific effect. And then the SC, again, the emulsion-based DRA improves the spreading. The surfactants are doing some work in here, even at the ground application, but addition of the emulsion-based DRA improves the spreading significantly over the ground-based and to some extent the UAV-based application rate or concentration. And then the EC, not surprisingly, spreads well no matter what. You might say that there might be some antagonism from the polymeric DRA inhibiting spreading, because the EC by itself without an adjuvant pretty much spreads the best of any of these concentrations of adjuvants. But again, the EC maybe doesn't need an adjuvant. And then here's a case where actually the CS does behave a little bit differently than the EC. At the UAV rate, it spreads significantly more than water, but addition of any of these adjuvants improves the spreading, and it is dependent on the concentration. So it's an interesting effect that the CS behaved the same as an EC everywhere until you got to spreading. Similar to the loaded SL didn't need an adjuvant until you got to spreading. So there's effects that you have to map out based on the function you're looking for in your adjuvant. Now here's some videos. I'm not sure how well they'll show up on over the internet, but what we have here is we have videos of a 500 to 600 micron drop impacting on a juvenile corn leaf. The one on the left is the unloaded SL at UAV rate, and then the one on the right is unloaded SL at UAV rate with the emulsion-based DRA. And what I want to show you is that, and if it doesn't show up, I'll try to narrate it. But when I hit start, there's going to be a drop that comes down kind of on the right-hand side of the frame, and then it's going to completely bounce off of the substrate. And this is a corn leaf, so this is an actual plant surface that we captured this video from. And so with no adjuvant, it doesn't, there's nothing to improve the retention. So if you add this adjuvant to this formulation, it might not be surprising, but we see good retention. So up here, this drop will come down in this area, and on the right-hand side, hit, impact, and retain on this leaf. So you can see that adjuvants sometimes do what they're advertised to do. In this case, it increases the retention greatly on a corn leaf, on a plant substrate. All right, what happens? I'm going forward. Okay, the next thing we looked at is the morphology of the dried deposits. And it's a little bit harder to interpret. We put a half microliter drop on a microscope slide, so on a glass slide, very hydrophilic. And then we took pictures of the deposits after they dried in the microscope. And I stitched them together most by hand because our stitching software was having a hard time stitching them together. So that's why they don't look as good as a typical stitched image. But the first one we look at is the unloaded SL at UAV rate and a ground rate. And then going from left to right is no adjuvant, the emulsion-based DRA, and the polymer-based DRA. And you can see with no adjuvant at a ground rate, you get kind of a nice clear deposit. And it doesn't change too much going to the UAV rate, except the concentration is higher. So you can definitely, it's more prominent. And actually the emulsion-based DRA, there's the same difference again, is that there's a lot more material there, but the actual morphology of the deposits, maybe not tremendously different. But then you get to the DRA, the polymer-based DRA, and you see a big difference in the way that droplet dried down, whereas I don't know how to explain exactly what happened, but you had some collapse and maybe you didn't pin the droplet on the ground rate, but at the UAV rate, you pin that droplet edge and it just evaporated to a coherent deposit. So I can't say for sure that would happen on a leaf surface, but there's the potential for differential deposit formation based on the adjuvant that you used and the increased concentration of UAVs. So here we have the loaded SL, and since that SL has a very large concentration of surfactant in it, it might not be surprising that you don't see a huge difference. And you pretty much just looks like you go from a low concentration to a high concentration from the ground rate to the UAV rate. You could try to pick out some differences, but I'd be hard pressed to say that there's a significant difference in the way these deposits form going from ground rate to UAV rate. And changing the emulsion-based DRA looks similar to the whether it's whatever concentration, and so does the polymer-based DRA. Now here's the suspension concentrate, and these are dark field because it's easier to see those. But at the ground rate with all of the adjuvants, you see kind of that typical coffee ring effect where you have a higher concentration in that contact line there where the droplet originally dried. Maybe a little bit less with the emulsion-based DRA, but it's hard to quantify. But then when you move up to the UAV rate, you see some pretty significant differences in the way those dried, in the sense that with no adjuvant or the polymer-based DRA, you still have that pretty significant coffee ring, although there's a lot higher concentration in the center because of the higher concentration of the droplet. But at the emulsion DRA, you see a more homogeneous deposit. So maybe, again, it may be important, may not be, depending on what you're trying to do, what kind of active you're working with, but it's a potential difference that you might not see if you've only ever evaluated your formulation at ground rate. And then the final data set that we generated was a wind tunnel test. So Croda has their own closed loop, vertically oriented, low speed wind tunnel. So that's a mouthful. And so we use that wind tunnel with a fine nozzle, an XR 11002 VS nozzle, operated at 43.5 PSI and a wind speed of 15 miles an hour. And it's sprayed concurrently. So we're not evaluating droplet movement, we're evaluating particle size distribution from that nozzle. And the driftable fines, the definition we used is droplets less than 105 microns in diameter as defined by the ASTM standard. And so here's the data as a whole. And we did several repeats of water just to make sure we weren't getting differences in the middle of the evaluation. So that's why there's a few dark blue bars. But here is the unloaded SL compared to water. And so the unloaded SL at UAV concentration does not reduce fines significantly. You add the emulsion-based DRA, and there's a significant reduction in fines. It's typical of this kind of DRA in this kind of nozzle. It's not the best, but it does significantly reduce fines. But what was somewhat surprising to us was that the polymeric DRA did not reduce fines. And there's two bars right there of the same test because we wanted to make sure that we didn't do something wrong. So then we went back and we did a titration to figure out if we could see where the effect happened. And this is what happened when we did that titration. So it goes from low concentration, about 1%, to up to the concentration that we saw the failure. And it's interesting that this is it turns on just above 20% concentration of that unloaded glyphosate IPA. And so this is something that if you don't get the concentration right that they're actually using in the field, if we did 20% and they went out and said, we're going to do 23%, we would say, oh yeah, that should be fine. But in this case, it wouldn't be fine if they're using this DRA. So it's important to make sure you're evaluating the conditions that are actually being sprayed in the field to know what the effect your adjuvant is going to have on your spray mixture. Now with the loaded SL, we didn't see any effect on drift control. And that's uncommon because with the ground application rate in this loaded SL, we typically see good drift control with either of these adjuvants. The polymer would be better than the emulsion, but we would see good drift control with both of them. So in this case, the concentration of surfactant is high enough and the concentration of active is high enough that it's defeating both types of DRAs. And you wouldn't necessarily know this until you go up to some of the really high concentrations that you might encounter in UAV applications. And then here we see the effect of the suspension concentrate. Now, at both ground and UAV concentration, the formulation does reduce fines compared to water to some extent, And then either DRA reduces the fines more. And this is more of a typical performance comparison of the emulsion versus the polymeric. The polymeric is certainly going to typically reduce fines more than the emulsion based, but based on the other things you're trying to do with your adjuvant, you would pick one or the other. And here with the EC and the CS, both those formulations reduce driftable fines to some extent without an adjuvant. And with an EC, that's not surprising. An EC is essentially an emulsion droplet. So emulsion droplets are known to reduce fines. So having an emulsion in there reduces fines. That's not surprising. The CS, it's got a potentially a harder wall, the shell of the capsule. So you don't necessarily know what to expect with that, but it does reduce fines somewhat similar to maybe the suspension concentrate. And then depending on the formulation and the adjuvant type and the concentration, you might get drift control depending on the formulation. So with the EC, if you add a significant amount of the polymer, a lot more than you would typically add at a ground rate, you can see some reduction in fines. And then with the CS, the same thing as well. Because but you need a higher concentration than you typically use at ground rate. And in the case of these, the surfactants in the EC or the CS may be interfering with the emulsion formed by the emulsion-based DRA. So maybe it's not surprising that they inhibit the performance of that adjuvant as a drift control adjuvant. So I'll go over this field trial. This is it's a small field trial. There's not a lot of data here, but it was just we wanted to see if we saw any effects from using these really high concentrations in a drone with the emulsion-based DRA. So it was done in Colombia, and it was the actives were glyphosate at 3 kilograms per hectare and 2,4-D at a 0.4 of a liter per hectare, and it's a local standard that they use for burn down. And then the NIS blend is the it's not actually an NIS blend. It was the emulsion-based DRA. And then there's some drone spray information. The model doesn't mean a lot to me, but it's a 6-rotor drone. And but it's important they have a capacity of 10 liters, and they were spraying 10 liters a hectare. So that's gives you an idea of what the kind of conditions they were using. They can spray a hectare with one load essentially, and it has 4 nozzles. It was flying at 1.8 meters, 4 meters a second, with a spray width of 6 meters, and the plot size was 240 square meters. So maybe a typical application in Colombia for this type of burn down. And what we saw was there was a significant effect on certain weeds with increasing the emulsion-based DRA adjuvant. So with no adjuvant, the herbicide worked, but the addition of an adjuvant certainly helped to kill certain weeds. And I'm not a biologist, so I can't tell you what those names are in common language. But certainly, and the effect you would notice is that the concentration of adjuvant that they maxed out at is much higher than the ground rate that we would typically recommend, anywhere from 0.25% to maybe 0.5% at the top for a ground rate. In this case, we're seeing an increase in efficacy all the way up to 1.5% of the adjuvant. So to wrap things up, I think what I hope we've demonstrated is that when you're selecting an adjuvant for UAV applications, the general understanding for ground applications is not necessarily applicable. It can be applicable, but it's not necessarily. In certain instances, the effects are either lost or not what you would expect. The adjuvants can still generally be used for the label roles, but you need to test your specific tank mix, your specific spray program that you're going to use it in to make sure that you still have the efficacy. And then we did this with kind of simplified tank mixes, only one formulation at a time. We talked about at the beginning. The complex tank mixes could be more challenging. So I think further work in this area should be done with real world tank mixes that introduce that added complication to the program. So with that, that's all I had. So I am happy to answer any questions that I'm able to.
All right, thank you, Jason. We've had a few questions roll in during the last 40 minutes or so, and And I know the focus of the talk was based around formulation type rather than some of those other factors. A set of questions came in about some of those other factors, right? Let's address Shengyu Long's set of questions, because I know in the arena of traditional ground-based applications, we do take downdrafts, nozzle types into consideration when it comes to spray drift outside the formulation type. So could you speak a little bit about the physics of the spray application as it applies to spray drift?
Well, first off, I'm a chemist, not a physicist.
Right.
But I think people are doing work in the area of evaluating how the downdraft from a helicopter type or multiple rotor type drone affects the application. It certainly could be advantageous, but as you're driving air down, that's also maybe creating updrafts outside of that downward force, which might create a cyclone effect. This is well outside of my area of expertise, but I think certainly people are looking at the way the swath is applied with water sensitive paper. I think there were a few talks on this at the ACS meeting with maybe Brad Fritz and people like that who look at swath width of aerial applications and are experts in this. And I know people are looking at this, and I would think that the design of the UAV will certainly have a significant effect on the characteristics of the application. But not all UAVs are overhead rotors. There are fixed wing aircraft UAVs. So, basically, when I said you want to evaluate the effect of your tank mix with your adjuvant and your application, it involves the equipment. You need to understand how the equipment set affects everything else that you're doing with your application. So it's not a very specific answer, but I think, yeah, I mean, certainly the equipment is going to have a big effect.
And from the formulator standpoint, the application method is most certainly at the top of the formulator's mind when it comes to developing these products. Have you? Another question from Shengyu was relevant to the wind tunnel. Have you found any anomalies between the traditional eddies that result from a ground application and the UAV downdrafts?
So that's actually a really interesting question, because the way our wind tunnel works is the wind circulates in a circular pattern, and the wind is moving downward and we're spraying downward. And the idea with our wind tunnel was laminar flow, so that you don't get any secondary breakup from wind currents or anything like that. So you're only evaluating the effect of the nozzle and the chemistry on the distribution you get out of the nozzle. But what you're asking is the downdraft from the UAV, is that going to affect any of this stuff? And I think the answer is probably, but in our wind tunnel, we don't have the ability to necessarily mimic that, because ours wasn't set up for that purpose. But I think that's an interesting thing that should be evaluated, and maybe some of the other wind tunnels out there might have a better ability, because they're horizontal, or maybe they can even fly a drone in their wind tunnel. I'm not sure our wind tunnel is big enough, the chamber, to fly a drone in it, but that's a very interesting question, and I would expect that there is some influence on that we can't measure. I know that that there's a lot of modeling done on the secondary breakup of droplets coming out of fixed wing aircraft, as crop dusters. So it's something that people have been able to evaluate, but we can't do that now.
Let's move on to a couple of the other factors that have nothing to do with the formulation, nothing to do with the equipment, but other environmental factors. There was a question raised on the effect of temperature and relative humidity on spray drift. Have we made any inroads?
I think the effect of relative humidity and temperature is going to be the same, independent of the application method. The difference just comes in the concentration of the tank mix and maybe the nozzle selection, and the height above the canopy. So if you were spraying, if you had a tractor that you could put that concentration in and spray at that height, at that speed or whatever, the effect wouldn't be different. It's just that if you have less water, it takes less time to completely evaporate. If you're using a smaller droplet, there's more surface area to evaporate from. So all those things that you tend to associate with UAV application of smaller droplets, longer flight path to the target, those sorts of things are working against you. And so, relative humidity and temperature are going to have the same effect independent of those things, but it's just the complication of the concentration, the flight path, and then some of the things we just talked about. The effect of the propellers, the rotors on the drone, and how that affects the path of the droplets. Those are sorts of things that I think need to be understood, and I'm sure there's people working on those things, but it's outside of the expertise. It's outside of our wheelhouse. We don't have the ability to evaluate.
That actually segues to another question on the board right now. If the drift reduction adjuvant is not very effective in the drone because of high concentration of the active formulation, but if it does improve efficacy, does that mean that we can use a more traditional adjuvant like MSO or crop oil concentrate instead of the emulsion DRA, conceivably?
Yeah, so we picked a couple of adjuvants because they were in our portfolio, and we knew that drift was a topic of interest for UAV application. But yeah, I think it's going to come down to the same considerations you have for any application you make. You want to pick the adjuvant that's going to give you the best efficacy while minimizing unwanted side effects. So if you're not worried about drift, which maybe you're not, and you're in the middle of a big field where you have adequate buffers or those sorts of things, you don't have to worry about drift, then you would pick an adjuvant that you would use for ground application. I think the takeaway is not that you need to use these specific adjuvants, it's that you might see unanticipated effects going from a ground concentration to a UAV type concentration. It's not to say that you have to use DRAs. It was just, we thought that would be of interest to the general people who are using UAVs.
Yeah, speaking of general people, we have a fantastic audience from the Agro division that spans a lot of different fields and agrochemical applications. Could you describe the difference between static and equilibrium ST measurements?
If you mean the difference between dynamic and equilibrium surface tension, yeah. So equilibrium surface tension is at long surface stages. So when you put a surfactant in water, it takes some amount of time to diffuse from the bulk to the air-water interface when you're measuring surface tension. So at equilibrium surface tension, you're doing that measurement under the assumption, and it's usually a good assumption, that you have an equilibrium situation. Everything that's going to diffuse the interface and orient there has done it. So the surface tension you're measuring is the surface tension at some long time frame. Dynamic surface tension, the way we measure it is you stick a capillary down into your surfactant solution and you blow bubbles. And then based on, there's some complicated math that I probably couldn't explain to you, but based on the pressure it measures in that bubble, it calculates the surface tension. And what it's calculating there is how much of that surfactant has diffused to the surface, how fast it diffuses to the interface. So equilibrium is just where it's going to get at the end of the day. Dynamic surface tension is how fast does it get to that interface. And so the surfactant type influences that. So a large, slow-moving polymer might get you a low equilibrium surface tension, but it'll take a long time to get to that interface, whereas a tiny alcohol ethoxylate, especially with, say, a branched hydrophobe, is going to get there really quick and reduce the surface tension quickly. So it's a different way of looking at it. And one of the reasons we highlighted that is because there is literature out there. It's been a long time. I think it was generated mostly in the 1990s, trying to look at what affects retention of agrochemical tank mixes onto leaf surfaces, and what they zeroed in on that's a reasonable circuit. It's not perfect, but is dynamic surface tension at some intermediate surface age between 100 and 200 milliseconds. And what they said is it takes from a nozzle to the leaf surface about 100 to 200 milliseconds to get there. Now, you could say that, well, that's not the same. That's not true for a UAV, since it's falling a lot longer, a lot higher distance. And we didn't actually consider that. I'm just thinking that now. But yeah, I mean, there's some lifetime where your droplet is formed and then it hits its target. And that surface tension at that surface lifetime is what we're interested in measuring, because we think that relates more or less to some degree to the retention you might expect from your tank mix.
Right. All right. Looking through questions. Yes, an early question, and I actually wanted to get around to this because it gets to actually one of my annoyances about the industry right now. It's the metric pounds per acre. I'm not sure where that conversation's going, but it probably it's probably going to be an outdated metric and measurement for amount of active ingredient applied by any various methods. So, what are the UAV rate and ground rate as a percentage? Can we give the audience a feel about that? Because and what is the difference between ground rate as a percentage and the application rate in pounds per acre?
Yeah, so the UAV rate, I mean, I might have been a little bit sloppy with the terms I used, but we basically said at the very beginning of the presentation, if you're using 100 liters per hectare on ground rate, you're maybe using 5 at UAV. So the difference in the application rate comes from if you're applying the same amount of herbicide to that hectare, if you're doing it 100 liters versus 10 liters, the concentration is much higher. You know, all these things are going to be determined by your specific application. So it's, but the pounds per acre is going to be constant. You know, however many pounds of herbicide you want to apply per acre for burn down, it's going to be constant. But the dilution rate is going to depend, you know, it depends on ground application. You know, how much water do you have available? How many times do you want to have to refill your sprayer before you run out? All those things are, you know, are variable. The use rate per acre of your active ingredient is, you know, essentially is for more or less constant for your particular use. The dilution rate is going to depend widely based on what kind of equipment set you're using and that sort of thing. So they're not interchangeable. But in general, UAV tank concentrations are going to be much higher than ground tank concentrations.
Fantastic. All right. We have 8 minutes left. Let's continue with the questions. Back to lab tests, Jason. What lab test for selection of adjuvant would be indicative of good performance and reduced drift with UAV and or ground applications in the field?
So what lab tests are good for what?
Would be indicative of good performance.
Well, yeah, and that's always the catch is that
right.
What kind of performance are you trying to enhance? If you're dealing with say a contact herbicide, you just want to cover as much of the plant as possible. If you're using a systemic herbicide, you want to enhance penetration. And the same thing for a contact versus a preventive versus a curative fungicide or something like that. It depends on what you want your adjuvant to do. So there's a lot of different lab tests. You know, surface tension and those sorts of tests are indicative of retention. I mean, they're not perfect, but they can give you an idea. And then a lot of people use Fran cells with isolated cuticles for uptake. So there's a lot of different methods, but it's all dependent on what your active ingredient does and how you want to achieve that result. So that's what makes adjuvants complicated. It makes them fun to work on, and you know, it keeps us in a job because if there's just one adjuvant out there that did everything, what would you need us for?
Okay. Yes, I'll go back up to Rajiv Sinha. Thanks for the great presentation. Just curious if the addition of DRA narrowed the curve with a lower relative span or just shifted the droplet curve towards the right, which would be a higher droplet size. Was there any difference in this aspect between the polymer and emulsion-based drift reduction?
Well, you know, I don't have the relative span data in front of me. I know that's a typical parameter that we measure. All I can say is in general, the polymeric-based DRAs simply shift the distribution, and there's narrowing of the span typically with the emulsion-based DRA. But that's a good question for the UAV studies. I know we have that data. I don't have it in front of me, but that's actually a good question. That's not something that I think we took a close look at because, and maybe we didn't highlight it because it didn't change. But I'll have to go back and look at that because I don't know off the top of my head.
All right. Trying to bunch a few things together here. Greg Dahl, How useful do you think swath displacement would be for maximizing deposition in the target area when using UAVs?
Greg, you're asking me a question way out of my area of expertise. I don't have an answer for that. I don't know. It's certainly something that you should bring up at the ASTM meeting if you're going to be there, because I'm sure Brad will be there and a lot of people who can answer these questions. But I don't have an answer for that. I apologize.
And we can follow up as well with we'll download a lot of these questions and be able to answer that offline as well. So we have that opportunity. I'm sure you and Croda will take that opportunity as we move forward. All right. Okay. Erdal Özkan had a remaining question. Did you compare efficacy from UAV applications with ground applications using the same adjuvants and with no adjuvants as well?
We did not in the test that we ran. I think we'd like to think we have a pretty good handle on how our materials perform in ground application. So we were interested to see if there was going to be any differences in the UAV type application. And I mean, I don't know if it should be surprising that a lot more surfactant improves efficacy, but I think it's something that we have plans to keep evaluating these sorts of things. So hopefully we'll be able to roll out more information in the future, but we don't have a side-by-side comparison at this moment.
We had an interesting one from Don Walchop about insecticides. I know adjuvants have been traditionally a herbicide, has traditionally been a herbicide thing, but there is cause to, on many occasions, to enhance the efficacy of insecticides. Have you looked at this technology with insecticides?
Well, I would say based on the question that Don asked, he probably knows more about this than I do. I have not done a lot of efficacy work in insecticides. I mean, the one thing I can say is that I do know that, similar to any active ingredient, based on the mode of action and whether it's systemic or contact or that sort of thing, or whether an insecticide needs to be ingested, you might want your adjuvant to do different things. Certainly, I know of one insecticide that you wanted to have a deposit that was kind of clumpy because you wanted to get a big enough dose to stop the insect from feeding. So there's all sorts of things out there, and I mean, I think the take-home message is that it's active dependent the type of adjuvant you want to use in your spray tank. And so there's a wide variety out there that do a lot of different things. I can't remember the number in the herbicide adjuvant handbook that Brian Young puts out, but I mean, there's so many adjuvants out there. There's so many to choose from. So I think there's a desire to tailor adjuvants for the effect and for the active ingredient now to reduce all sorts of things, off-target movement, but also application rates if you can, that sort of thing. So yeah, like anything, it's going to be specific to your active ingredient.
A couple questions on spray tank composition and formulation composition here. We can bunch two of these together. Have you looked at adding a dye to any of your on-field applications to see where the drift goes, and have you considered higher molecular weight polymers and the effect on drift?
Yes. So we've put cards out, like water sensitive paper cards out in the field, and I don't know if we've used any dyes. I'm not sure, but we've made attempts to try to semi-quantify drift in those situations. I'm not sure that we were confident enough in our data to share it. So while we've tried to do it, we've always fallen back on the ASTM defined driftable fines at 0.05 microns. So if we measure that, it'll give us some indication of the likelihood of drift. The actual infield measurements are a lot more complicated, so we're not as confident in that data. As far as higher molecular weight polymers, you're fighting drift control versus usability. As the molecular weight continues to increase, it's harder and harder to make a easily used formulation. That's why some people have gone to putting dispersing a polymer in oil that you then add to the tank, then the polymer hydrates, because there's a lot of complications about using high molecular weight polymers and making a solution of those at a concentration necessary to use it.
Okay. Great. Well, that takes us to the top of the hour. Thank you, Jason, so much for presenting here. And thank you to the audience. About 70% of you hung on for the entire Q&A, which is fantastic. Great number of participants for this webinar. And thank you so much for your participation. I would like to thank Jason again for an excellent job, as well as his company, Croda Inc., the ISAA Agrochemical Network, Eurofins Agro Science Services, and our webinar coordinator, Kyle Sawyer. Thank you so much to all of you. You may be asked as a member of our audience to complete a follow-up survey after the webinar, and we look forward to that feedback. Our next webinar is on October 19th at 12 o'clock in the eastern part of the US, featuring Brian Kuntz, who will speak on the changing landscape of regulations on industrial hemp. Our facilitator will be a speaker from earlier this year, Toy Fu, who is engaging and fantastic. She will be a fantastic facilitator in this field of cannabis and hemp. Thank you all so much for your attention, and we will see you on October 19th.